Welcome to the course on biostatistics and design of experiments. Today we will continue on the t-test. Like I had mentioned that t-test does a comparison of means. Okay, so if the mean of one sample and you have a mean of another sample, you want to know whether they come from the same population or they come from different population, and so on actually. So basically t-test compares means. So there are three different types of t-test: one sample t-test, two sample t-test and pair t-test. So in one sample t-test, what you do is you take a sample and the mean which you get, you compare it with the population mean, okay, and you find out whether this sample mean comes from this population or not. In a two sample t-test, you are comparing two sets of samples. For example, if I am comparing drug A and drug B performance, then I will get some mean for sample set 1 and I will get some mean for sample set 2, and I would like to see whether there is any statistically significant difference between these two means or not. In the pair t-test, you use the same subject for performing the experiment. For example, if I am performing clinical trials and I have 10 volunteers, I may give drug A to the 10 volunteers, and after a few days I may give drug B to the same 10 volunteers, and I will see the change. So theoretically, if A and B perform in the same way, the difference should be 0. Okay, that is called the pair t-test. Okay, let us continue with some problems, because problems are very important. Problems give you an idea about how to attack these type of situations, and you need to know how to use the tables, you need to know when to use a one sample t-test or two sample t-test, when to use a one tailed or two tailed, how to create the null hypothesis and alternate hypothesis, and so on actually. Okay, so the mean heart rate of 20 rats is say 282 with a coefficient of variation of 15%. What is coefficient of variation? 100 sigma divided by mu. Okay, during anesthesia the mean rate becomes 240. Okay, so it looks like it's gone down, but the CV is the same. Is the decrease in heart rate significant? Okay, we need to find out whether the decrease in the heart rate is significant. Give 95% confidence limit for the change in the heart rate. That means it's the change, that is 240 minus 282 or 282 minus 240. What is the confidence interval? Although we say 282 minus 240, the change is 42, but then there is always going to be a region of confidence, because in any mean will always have a standard deviation. Okay, let us go about solving one at a time. So coefficient of variation is given by 15%. So 15 is equal to 100 into S, the standard deviation, divided by x bar. Okay, so as you can see, 282 is the mean, that is x bar. So from there I calculate, yes, simple. Okay, so I just rearrange. So S comes out to be 42.3. Now the variance S square is equal to square of that, 1789. Now I can calculate the standard error of the mean, okay, by 20 here, right, by dividing. If you remember, what is the standard error? S by square root of n, or the square of the standard error of the mean will be S square divided by n. So that is what I get, 89.45. Now CV is the same for the anesthesia group also. So the standard error will be the same for the anesthesia group. Do you understand this so far? Okay, so I know CV, I take 282 here x bar, so I calculate S. Okay, that is the standard deviation. Now the standard error of the mean, I just have to divide by n, and then later on I need to take square root, but right now we are not taking square root, we leave it like that. Now CV is the same for the anesthesia group also, so standard error for the anesthesia group also will be the same. Okay, now let us formulate our hypothesis. H naught mu equal to mu naught, that means there is no difference. In HA we say mu is less than mu naught. If you read the problem, decrease in heart rate. Okay, so we are saying mu is less than mu naught. So what do? We take our T equation, T is equal to x bar minus mu naught divided by S by square root of n. Okay, you remember this equation, right? T is equal to x bar minus mu naught divided by S square root of n. Okay, this is called the standard error, mu naught is the population mean and this is the sample mean t. Degrees of freedom will be n minus 1. We calculate the t and then we compare the table t. If the t calculated is less than the table t, we accept h naught. If the t calculated is greater than the table t, we reject the h naught. Here it is a one tailed test. Please remember, because we are talking about this type of situation, we are not saying mu not equal to mu naught, that means less or more, but we are specifically talking about mu less than mu naught. Okay, so it is a one tailed test, simple. So what we do is we t calculate, I know 240, the other one is 282. So if you remember, we got 89.45, so square root of 89.45 is what I need to put here. So 240 minus 282, I will get minus 4.44. Now let us go to t table with okay, t table. If I go for one tail test for p is equal to 0.05, okay, one tail test p is equal to 0.05. So I need to look into this region, right? Okay, so I need to look into this region. Okay, so I get the 9 degrees of freedom, because there are 10 rats, so 10 minus 1 is 9, so it is 1.833. So p from the table is 1.833, t calculated is minus 4.44, so it is greater, so we reject the null hypothesis at p is equal to 0.05. So we need to accept the alternate hypothesis. That means the heart rate has decreased because of anesthesia, and this decrease is significant at 95% confidence interval. So you understand this. Okay, it is very simple. Okay, so we need to use this table. As I said, if you are talking about one tail test, use the top numbers. If you are using two tail test, we use the bottom numbers. So when I said 0.05 for two tail, I mean sorry, one tail, I used this, whereas if I had said that for a two tail, I would have used this. As I said before also, so two tail includes the outside area on both sides of my normal distribution curve. So when I divide, if I want to consider only one side, obviously 0.05 by 2, that is why here it is 0.025. Okay, so you know how to use. Now I want to know change in the heart rate. So what is the change? 42 is a change in the heart rate. Okay, so I need to calculate the overall standard error. Understood? So the overall standard error, how do I do? I have both are same, right? 89.45, this is the variance of that, 89.45 divided by 89.45, that comes out to be 178.9. Okay, so I take a square root of that, I will get 13.4. Okay. Now I need to consider all the data sets. So I have one set is 10, I have 9 degrees of freedom, other set is 10, I have 9 degrees of freedom, now I have 18 degrees of freedom, and I need to use two tail test, two tail table, because we are talking about plus or minus here. You remember this equation, right? Mu equal to x bar plus or minus t d of s by square root of n. So I use both the regions, p is equal to 0.05 with 18 degrees of freedom. So I read out this 2.101. Okay, I take 2.1 and 13.4 comes from here, and 42 is the change in heart. So the confidence limit for the change in heart at 95% confidence is 14 to 70. Do you understand the second part of the problem? So the second part of the problem is you are supposed to find out the confidence limit for the change in the heart rate. Change in the heart rate is, originally it was 282, now it became 240. So change. Now to find the confidence limit, I use this equation, if you remember this. So it is a plus or minus t s by square root n. Okay. Now we have 89.45 for one set, 89.45 for the second set. So total will be 178.9. So I take a square root here, it becomes 13.4. Okay. That is the standard, this whole portion. Okay, this whole portion. Now t, I use 18 degrees of freedom. Do you understand why? Because the first set has 10 rats, 9 degrees of freedom. The second has 10 rats, 9 degrees of freedom, totally 18 degrees of freedom. I use two tail because this is a plus or minus we are doing. So, and then t comes out from the table, so 0.05, 18 degrees of freedom, 2.101. So, I substitute here, I put 13.4. So, when I do that, I get the change in the heart rate, the limit confidence limit for the change in the heart rate at 95% confidence is 14 to 70. So, it is an interesting problem, very useful problem. We do quite a lot of these type of studies in clinical trials. We have a drug, you do give the drug and you see changes, okay, you know the original population and you are looking at change, then you are trying to see whether the change is statistically significant or no. Okay. So, this is very, let us look at another problem. The concentration of a drug in the brain of 6 rabbits is determined after 5 minutes after administering the drug. Okay. So, you are injecting a drug on 6 rabbits, then after 5 minutes you are measuring their concentration. It comes out to be 40.2, 38.7, 41.6, 40.5, 43.2, 39.5. Okay. Now, calculate the 99% confidence interval for the true mean concentration, okay, that we can do. The mean concentration of the same drug in rats are reported to be 45 milligram per gram. Now, this is the data, sample data from rabbits. This is the data which they got from rats. Is there a statistical significance difference between these two data? Okay. So, two parts, one is calculating the 99% confidence is very simple. So, we can calculate x bar from this data, okay. Then for 5 degrees of freedom with 99% confidence, from the table we can calculate t, and then we can calculate the standard error, that is s by square root of n, that will give you my confidence limit, right. Okay, then the second part of the problem, okay. So, let us look at this average. So, the average comes out to be 40.6 and S is equal to 1.6. Of course, we can calculate the CV also in this case, but mainly we are more interested in this, okay. So, we take it as 40.6, we take this as 45, okay, then you know the S, then divided by square root of 6, and then degrees of freedom is 5. If t is less than the t calculated is less than the table t, accept H naught, t is greater than the table t, reject H naught. We are doing two tail test because the question is in rats it is 45 milligram per gram. Is there a statistical difference between these two data? Okay, is there a statistical difference? So, the H naught will be equal to mu equal to mu naught, H alternate will be mu is not equal to mu naught. Okay, and so we do that. We do the two tail test. Okay, for 5 degrees of freedom, 99% confidence. Let us look at the table. Two tail test. 99% confidence means it is 0.01. For 5 degrees of freedom, you get this here, 4.032. Okay, 4.032. So the so this is the equation here, x naught minus mu naught. So we do 40.6 minus 45, and then your standard deviation is 1.6 for the data. So divided by square root of 6, that will come to minus 6.73. The data is significantly different. Okay, data is significantly different. So that means we can reject the null hypothesis. That means we accept the alternate hypothesis. Now the difference in the mean 40.6 minus 45 is 4.4, right. So confidence interval on the mean. So obviously t into s divided by square root of n. Okay, t is 5 degrees of freedom. Okay, so we get this, and then s square root of n. So we get a confidence interval on the mean as this actually. So the difference in the mean is this, confidence interval on the mean is this. Okay. Now we can use the graph pad also to do the same calculation. Okay, we can use not only the graph pad, we can also use our Excel also to do the calculation. Okay, shall we look at Excel? Okay, quite simple. So let us go back to Excel. So the data is 40.2, 40.2, 38.7, 41.6, 40.5, 43.2, 39.4. Okay, so we have sorry 38.7 and so this data is not there. Okay, so we have 6 data sets. Now the command, if you remember, we go to this and there is something called a t test. Okay, so when you look at the t test, what are the various things? Array 1, so we give the data set here. Okay, and then we give the array 2, so here we give the 45, we gave a two-tailed test, and then here we give a pair or two sample t test. Of course we can't do, as you can see, we cannot do unfortunately we cannot do in Excel this type of calculations, unfortunately, but we can use the other software. Okay, here as you can see, descriptive statistics, t-test here, the graph pad, here you have the one sample t-test. So we can give the data here 40.2, then 38.7, then 41.6, and then 40.5, 43.2, 39.4. Okay, then we say we are comparing with 45. Okay, so we have 6 and then mu naught is here. So now when you say calculate now, of course this gives you only at 95% confidence interval. So okay, this is doing at the p value comes out to be 0.0011. Okay, and it's a statistically significant difference, as you can see here. Okay, even at 95% confidence interval also it will come out to be statistically significant difference, because if you look at the table here, if you look at the table here, for 5 degrees of freedom, for 99% confidence interval it is 4.032, for 95% confidence interval it is 2.571. So your t value which you calculate is quite high here. Okay, 6.692. Okay, so obviously that number is very high. Okay, your t value which you are calculating is pretty high. So obviously that number is much higher than the table t, whether it is at 95% or whether it is at 99%. So you see that with the Excel we do not have a way of calculating the t test for a one sample t test, whereas with the graph pad we can do this type of calculation with the ease. Now let us go to next type of test, that is called a two sample t test. That means I have two drugs, I am comparing the performance of two drugs and I am trying to tell whether there is a statistically significant difference or not, or I am comparing a control and a drug A which I have introducing in the market, or I am comparing already existing drug and another drug, or I am comparing the performance of a drug on a male population and a female population. So we have two sets of samples, so you will have a x1 bar and x2 bar, that is two means, and then we are trying to see whether there is whether each of these sample means come from the same population or they come from different population. Okay, for example, we are telling a drug is tested in rats for lowering blood glucose level. Okay, this is drug treated rats. So, this is the glucose level, and whereas this is the control rats, this is the glucose level. Okay, so we have two sets of samples. Okay, 6 samples for drug treated rats, 6 for the control. Now, is the drug effective in lowering the blood glucose level? For example, imagine this sample comes from one population like this. Imagine this sample comes from another population like this. Now, are these populations are overlapping so much that we can consider it as one single population, or they are different? That is the whole idea of this. And is the drug effective in lowering? That means this is a single tail test. Okay, for totally we have we have a t value. Okay, so we can find out, and we can tell whether there is a statistically significant difference by saying whether the drug is lowering or there is no difference. So, the hypothesis, the null hypothesis will be mu t, okay, is equal to mu c. That means test and control, we say drug treated we call it test, c means control, whereas alternate could be mu t less than mu c. Okay. So, this is the equation by which these things are calculated. Okay. So, we suppose we have a number of data points for one set of sample, number of data points for another set of sample. So, the degrees of freedom will be this plus this minus 2. Okay, that is why in this particular problem, so we may have 3, 4, 5, 6, 3, 4, 5, 6 plus 5 is 11, 11 minus 2 is 9 degrees of freedom. Do you understand? So, here we have taken 6 data points for drug treated, here we have taken 5 data points. So, the advantage of 2 sample t test, I could have different sets of samples also. In fact, this particular equation, if you look at this equation very carefully, I can have any value of NH, I can have any value of NL. So, it need not be the same. Okay. So, t value is given by this equation xh minus xl, that means mean of one data set minus mean of another data set or sample set, 1 by NH plus 1 by NL square root, and then we have something called SP here. Okay. This is the standard error. If you look at it very carefully, this for one sample we used to have SP divided by square root of n. So, this is almost analogous to that. Here we have square root of 1 plus NH plus 1 by L SP, but here SP it looks slightly different. NH minus 1 SH square plus NL minus 1 SL square divided by NH minus 1 plus NL minus 1. That is the equation for SP here. So, there are some similarities if you look at it, this equation and the normal t equation for one sample t test and so on. So, it is quite simple. So, we have 2 data sets, I get the mean of this, I get the mean of this, I get the standard deviation of this, I get the standard deviation of this, NH is equal to 6, NL is equal to say 5. So, I substitute the standard deviation here, square it, here it will become 6 minus 1, 5 minus 1. So, here 1 by 6, 1 by 5, and then here you get the mean of both the data sets and you get the answer. So, we can use a simple Excel to calculate means and standard deviations, and that is what I will do. That is, the whole idea is we try to calculate t using fundas. It is easy to use softwares, whether Excel command like t test, it is easy to use the GraphPad like software or any commercial software, but then you need to know what is the underlying equation. That is very, very important, and that is what I would like to emphasize on. So, with drug, for the numbers are here, okay, 6 numbers are here. Control, that means you are not giving drug, there are 5 numbers. So, we can get the average. Average is very simple, you add all of them divided by 6, you add all of them divided by 5. Standard deviation of this data set, again you can use Excel, there is a STDEV function, and here also. So, this gives you the standard deviation of this, this gives you the standard deviation of this. Okay. Now, you are squaring this also, because I need to get here, right. So, I am squaring this and then I am adding this. Okay. I am squaring this and I am adding this, and then from there I calculate the t using this formula. Okay. The denominator is 1 by 6 plus 1 by 5 square root here. Okay. So I calculate this, so from there I can calculate the t calculated. So it comes out to be minus 1.89. Now t table is how many degrees of freedom? 6 plus 5 is 11, 11 minus 2 is 9, so 9 degrees of freedom. You go to the t table, it is a single tail 95%, because why single tail? Is the drug effective in lowering? Okay, so it is a single tail test. So we go to the table, it is a single tail, 95%, 9 degrees of freedom, it comes to 1.833. Okay, so the t calculated should be greater than 1.833, but the okay, so it comes to 1.89. So we can reject the null hypothesis. Please note, it is only marginally higher. Okay, 1.89 and 1.833 is not very high, whereas if you take a 99% confidence interval, that is 0.01. Okay, for 9 degrees of freedom it is 2.82, t table is higher, so we will not reject the null hypothesis. So it is very close problem, very close conclusion. Okay, so I would not go with close conclusion, I may do more experiments to be very sure. We understand in this problem with 95%, 1.833 is a table, so 1.89, so I can reject the null hypothesis. With the 99% and one tail test, you get much higher, greater than 2.3, so you will not reject the null hypothesis, and even 1.83 and 1.89 are very close. So although you can say I will reject the null hypothesis at 95% confidence, I would not go too much. I may try to do more experiments so that we get a better difference between the t calculated and the t table. We understand. So this is a very close call actually. Okay. So the Excel also can do this, and I showed you last time just a few minutes back. Excel cannot do a one sample t test, but it can do a 2 sample t test, it can do a paired 2 sample t test, it can do a 2 sample t test when equal variance, 2 sample t test when the unequal variance. So the commands are array 1, array 2, tails and type. Array 1 is one first data set, array 2 is second data set, tails is 1 means is 1 tail, 2 means 2 tail. Okay. So from Excel we get 0.043, that is the probability. So it is less, so we can say we will reject the null hypothesis like here. Okay. We can reject the null hypothesis, but it is very close call. Okay. So how do you do it in Excel? So we just put this data inside, and then we do the calculations. Okay. So we say 2.02, 1.71, 2.04, 1.5, 1.83, 1.69, then here 1.71, 2.04, then 2.15, 1.92, 1.78, 2.04, 2.22. So we use the same command TTEST. So we give the first data set and then comma, we give the second data set, then we comma, it is a one sample t test, and so we can give a equal variance or unequal variance. So if I put 3, 0.043, so I basically I have given it as 3, that means unequal variance. So I can even give it as equal. So for unequal variance I am getting 0.43. Yes, the variances are unequal, as you can see. Okay, standard deviations are unequal here. Okay, so it is giving 0.043. So we we reject the null hypothesis and accept the alternate hypothesis. Same thing we can do with the GraphPad software also. Okay. But you see it's going to be very close in GraphPad software. Okay. So what do we do? How do we do this in GraphPad? Let us go back there. So here we have the t-test command, compare two means. So we go there and then we continue. Because the data, the t calculated and t table are very close to each other, some softwares may say it is not statistically significant, some software may say statistically significant. So especially you need to watch out if the data is very close to each other, that is t calculated and t table, it is better to do more experiments to have more confidence in your conclusion. Okay. So we will continue on this t test in the next class also. Thank you very much.